Welcome! In this session, we'll tackle LeetCode problem number 1047, remove all adjacent duplicates in string. This is a popular string manipulation problem that challenges us to efficiently remove all adjacent duplicate characters from a given string. By the end of this walkthrough, you'll gain a deeper understanding of effective strategies and their trade-offs. Let's dive in. The problem asks us to process a string made up of lowercase English letters and remove consecutive, adjacent duplicates. A duplicate is defined as two characters that are next to each other and are the same. The goal is to repeatedly remove these duplicates until there are no adjacent duplicates left in the string, and then return the final result. For the input, we are given a single string s, and the output will also be a single string representing the processed result. For example, if the input string is a baka, the output after removing all adjacent duplicates will be ca. Here's how the process works for the first example. Starting with a baka, we first remove the adjacent duplicates bb, which leaves us with aka. In the next pass, we remove the adjacent duplicates aa, resulting in ca. Since there are no more adjacent duplicates, the final result is ca. Now, consider the second example where the input is asci. First, we remove xx, leaving us with asi. Then, we remove zz, resulting in I. No further adjacent duplicates exist, so the final result is I. For the third example, the input is abba. In the first step, we remove the adjacent duplicates aa, leaving ba. Next, we remove bb, which gives us aa. Finally, we remove the last aa, leaving an empty string. Since no adjacent duplicates remain, the final result is an empty string. The problem also imposes certain constraints. The length of the input string will be between 1 and 100,000, and the string will only contain lowercase English letters. This means we need an efficient solution to handle large inputs. Now, let's consider some edge cases. If the input string has only one character, such as a, there are no adjacent duplicates, so the output will be the same as the input. Similarly, if the input string contains no adjacent duplicates, like abc, the result will again be the same as the input. On the other hand, if the entire string consists of just one repeated character, such as aaa, the result after removing all duplicates will be an empty string. Finally, if duplicates are interspersed but not adjacent, such as in abababab, no removal occurs, and the output remains the same as the input. When tackling LeetCode problem number 1047, we start by considering several approaches to remove all adjacent duplicates from a string. The brute force approach is the simplest method to understand. Here, we repeatedly iterate through the string, identifying any adjacent duplicate characters. Whenever a duplicate pair is found, it's removed, and the process restarts from the beginning of the modified string. This continues until no duplicates remain. While this approach is conceptually straightforward, its major drawback lies in its inefficiency. Each removal involves reconstructing the string, which can result in a time complexity of O(n) squared, in the worst case. Additionally, it requires O(n) space for the reconstructed string, making it far from optimal for longer inputs. This inefficiency highlights the need for more advanced strategies. An optimized approach to solve this problem is to use a stack-based method. The key intuition here is that a stack provides a way to efficiently handle adjacent duplicates during a single traversal of the string. As we process the string character by character, we push each character onto the stack unless the top of the stack matches the current character, which indicates a duplicate. If a duplicate pair is found, we simply pop the top of the stack, effectively removing the duplicates. The remaining characters in the stack at the end of the traversal represent the final string with all duplicates removed. This approach is both time efficient and clean, achieving a linear time complexity of O(n), because each character is processed only once. The one trade-off is the O(n) auxiliary space required for the stack, but this is a reasonable compromise given its simplicity and efficiency. Additionally, a variation of this method using a two-pointer approach can provide an alternative solution. In the two-pointer approach, the goal is to save space by avoiding the use of additional data structures like a stack. Instead, we use a right pointer to overwrite the input string in place as we process it. For each character, we check whether it matches the previous character in the result portion of the string. If a duplicate is found, the right pointer is rewound to remove the duplicate pair. Otherwise, the character is written into the result. This ensures that the input string is progressively updated without needing extra space. The primary advantage of this method is its space efficiency, achieving 1 space complexity. However, it modifies the input string, which may not always be acceptable depending on the problem constraints or real-world use cases. While this approach is efficient in terms of both time and space, its in-place modification of the input makes it less flexible than the stack-based solution. The stack-based approach stands out as the chosen solution for this problem because of its balance between simplicity, efficiency, and practicality. One of the key observations that makes this approach effective is that adjacent duplicates can be handled naturally using a stack structure, where duplicates are cancelled out by popping elements. By traversing the string just once and leveraging the stack, we avoid the repeated traversals and reconstructions required in the brute force method, bringing the time complexity down to n. This makes the stack-based approach significantly faster for larger strings. The aha moment here is realizing how the stack eliminates unnecessary work while still being intuitive to implement. Although the auxiliary space required for the stack may seem like a drawback compared to the space efficiency of the two-pointer method, it is a reasonable trade-off because the stack approach ensures immutability of the input string, which is often a desirable property. In terms of complexity, the stack-based approach provides a robust and scalable solution to the problem. The time complexity is n, as we traverse the string once and perform constant time stack operations for each character. The space complexity is n, due to the stack, which stores characters when necessary. This balance of time and space efficiency, coupled with its intuitive implementation, makes the stack-based approach an excellent choice for solving this problem. It's a method that is not only efficient in practice but also conceptually straightforward, making it widely applicable for similar problems involving duplicate removal or adjacent element cancellation. The goal of this problem is to process a string and remove all adjacent duplicate characters repeatedly until no such duplicates remain. For example, given the input abaka, we first remove the duplicate bb to get aka, and then remove the duplicate aa to finally get ca. To solve this efficiently, we use the stack data structure because it allows us to handle repetitive or nested operations in a linear manner. Here's how the algorithm works. First, we initialize an empty stack, which will be used to store characters as we process the string. This stack is crucial because it helps us keep track of the most recent character and makes it easy to compare with the next character. Then, we iterate through the string, processing each character one at a time to check for adjacent duplicates. During the iteration, if the stack isn't empty and the top of the stack matches the current character, it means we've found an adjacent duplicate. In this case, we remove the top character from the stack, which simulates removing the duplicate from the string. If there's no match, we simply push the current character onto the stack to keep building our result. Once the iteration is complete, the stack will contain all the characters of the final string in the correct order, with no adjacent duplicates remaining. At this point, we convert the stack back into a string using the join operation, and this gives us the processed result. The stack plays a key role here because it allows us to efficiently track and resolve duplicates in a single pass through the string, avoiding the inefficiency of repeated scans. This makes the stack-based approach significantly more optimal than brute force methods. The efficiency of this algorithm comes from the fact that each character is pushed onto and popped from the stack at most once, making the time complexity n, where n is the length of the string. The space complexity is also n, in the worst case, where all characters are unique and the stack grows to the size of the string. Additionally, the algorithm handles edge cases gracefully. For an empty string, it simply returns an empty string. If the string has no duplicates, it returns the original string as is. And if the string consists entirely of duplicates, it removes all characters and returns an empty string. The stack is the primary data structure used here, as it helps track characters and resolve adjacent duplicates efficiently. The input string is processed character by character, and the result string is formed by converting the stack back into a string. While this approach is already efficient, there are opportunities for further optimization. One potential optimization is to modify the string in place instead of using a stack. This could save additional space, but it might make the implementation more complex. Another idea is to use batch removal techniques for cases where adjacent duplicates form long blocks. For example, a two-pointer method could be used to efficiently remove such blocks in a single pass. Here's a pseudocode representation of the stack-based approach. We first initialize an empty stack. As we iterate through the string, we check if the stack isn't empty and if the top of the stack matches the current character. If it does, we pop the stack to remove the duplicate. Otherwise, we push the current character onto the stack. After processing all characters, we join the contents of the stack into a string and return it as the result. This pseudocode provides a clear, step-by-step outline of the algorithm and highlights its simplicity and effectiveness. To analyze the complexity further, the time complexity of this algorithm is O(n), because each character is processed exactly once, either pushed onto the stack or popped from it. The space complexity is O(n) in the worst case when all characters are unique, and the stack grows to the size of the string. Let's walk through an example using the input Abaca. Initially, the stack is empty. First, we push A onto the stack. Then, we push B, but when we encounter another B, we pop the stack since it's a duplicate. Next, we push A again, followed by C. Finally, we encounter another A, which doesn't match the top of the stack, so we push it as well. By the end, the stack contains CA, which represents the final result. This example demonstrates how the stack efficiently handles duplicates and ensures that the final string is free of adjacent duplicates. The final result of the example is CA, which is formed by converting the stack back into a string after processing all characters. This approach highlights the power of using a stack for solving the problem. The stack's ability to efficiently track and compare characters gives us a clean and optimal solution with linear time complexity. By processing each character only once and handling duplicates in a single pass, the algorithm achieves both simplicity and efficiency. Overall, the stack-based method is an excellent choice for this problem, offering an elegant and effective way to remove all adjacent duplicates from a string. This Python solution efficiently removes all adjacent duplicates from the input string using a stack-based approach. Here's a detailed explanation of the code. 1. Class and function definition. The remove duplicates function is implemented as part of the solution class. This function takes a string s as input and returns the processed string with no adjacent duplicates. 2. Stack initialization. A list named stack is initialized to simulate a stack data structure. The stack will be used to keep track of characters as we traverse the input string. 3. Iterating through the string. The function iterates through each character in the input string s using a for loop. During this traversal, each character is either added to the stack or used to remove adjacent duplicates. For removing adjacent duplicates, inside the loop, the function checks if the stack is not empty and if the top character in the stack, represented by stack-1, matches the current character. If these conditions are true, the top character is removed from the stack using stack.pop. This effectively removes the adjacent duplicate. 5. Adding non-duplicate characters. If the current character does not match the top of the stack or the stack is empty, the character is added to the stack using stack.append, char. This ensures that non-duplicate characters are preserved. 6. Constructing the result. After processing all characters in the input string, the stack contains the final string with no adjacent duplicates. The join method is used to concatenate the characters in the stack into a single string, which is then returned as the result. ###edge cases. If the input string is empty, the function returns an empty string since there are no characters to process. If the input string contains no adjacent duplicates, the function returns the string unchanged. If all characters in the string are duplicates, the function removes all of them and returns an empty string. ###time and space complexity. The time complexity is O(n), where n is the length of the input string, since each character is pushed or popped from the stack at most once. The space complexity is O(n) in the worst case, as the stack may grow to the size of the input string if there are no duplicates to remove. This implementation is efficient and handles all edge cases effectively, making it a robust solution to the problem. This is the Java implementation of the LeetCode problem: remove all adjacent duplicates in string. The logic mirrors the Python solution, leveraging a stack-like behavior for efficient processing. In Java, we use a string builder to simulate the stack for its efficient append and delete operations. The code iterates through the input string, checking if the last character in the stack matches the current character, and removes or appends accordingly. The final result is converted back to a string and returned. To solve this problem, we use a stack to help us efficiently remove adjacent duplicates. Let's work through example 1, where the input string is a baka. First, we initialize an empty stack. We then begin processing the characters one by one. Starting with the first character, the stack is empty, so we simply append it to the stack. The stack now contains a. Next, we process the second character, b. The stack is not empty, and the top of the stack, which is a, does not match b. So, we append b to the stack, making it a b. Now, for the third character, b, we check the stack again. This time, the top of the stack, b, matches the current character b. Since they match, we remove the top element by popping b from the stack, leaving it as a. Moving on to the fourth character, we see that the top of the stack, matches the current character a. So, we remove the top element again, leaving the stack empty. Next, we process c. Since the stack is empty, we append c, resulting in c. Finally, the last character is a. The top of the stack, c, does not match a, so we append it to the stack. At the end, the stack contains c, a. By joining the stack's elements, we get the final output string ca. Now, let's look at example 2, where the input string is ASCII. We start by initializing an empty stack. The first character is a, and since the stack is empty, we append a. The stack now contains a. Next, we process z. The top of the stack, does not match z, so we append z, resulting in z. Moving on to x, the top of the stack, z, does not match x, so we append x, making the stack z, x. For the next character, another x, the top of the stack, x, matches the current character x. So, we remove the top element by popping x, leaving the stack as z. The following character is z. This time, the top of the stack, z, matches z, so we pop z, leaving the stack with a. Lastly, we process y. The top of the stack, does not match y, so we append y, resulting in the stack, y. Joining the elements of the stack gives us the final output string I. For example 3, the input string is aba. As usual, we begin with an empty stack. The first character is a, and since the stack is empty, we append a, making the stack a. The next character is another a. The top of the stack, matches the current character a, so we pop a, leaving the stack empty. Moving to b, the stack is empty, so we append b, resulting in b. The next character is another b. The top of the stack, b, matches the current character b, so we pop b, leaving the stack empty again. Now, we process a. Since the stack is empty, we append a, making the stack a. Finally, the last character is another a. The top of the stack, matches the current character a, so we pop a, leaving the stack empty. At the end, the stack is empty, so when we join its elements, we get an empty string as the final output. The time complexity of the stack-based solution is O, n, where n represents the length of the input string. This efficiency comes from the fact that we traverse the string exactly once using a single for loop. During this traversal, each character is either added to the stack or removed from it, depending on whether it forms an adjacent duplicate. Both of these operations, append and pop, are constant time operations, O1, when performed on a Python list. After finishing the traversal, we need to construct the final output string by joining the remaining characters in the stack. The join operation in Python is proportional to the number of characters in the stack, which in the worst case can be as large as n. Therefore, this step adds another O, n, to the time complexity. Since the traversal dominates in terms of computational cost, the overall time complexity is O, n. The space complexity of this solution is also O, n, as the stack used to store characters can grow to a maximum size of n in the worst-case scenario, where no adjacent duplicates are found and all characters are pushed onto the stack. The input string itself does not contribute to additional space complexity, as we are not creating a copy or modifying it directly. However, the output string, which is created by joining the stack, can be as large as the input string in the worst case, contributing another O(n) to the space complexity. When compared to a brute force approach, the efficiency of this method becomes evident. A naive solution would involve repeatedly scanning the string for adjacent duplicates and removing them until no duplicates remain. This leads to a time complexity of O(n squared, in the worst case due to repeated passes over the string, each taking O(n). Both approaches, however, share the same space complexity of O(n), as intermediate storage is required in either case. The stack-based approach offers a significant improvement over the brute force method by reducing the time complexity to O(n). Each character in the string is processed at most twice, once when it is pushed onto the stack and possibly a second time when it is popped. This ensures a linear time complexity. The space complexity remains O(n), as the stack can still grow to store all characters in the input string if no duplicates are removed. Now, let's analyze this approach across different scenarios. In the best case, all characters are unique, and the stack grows to size n without any popping. The time complexity is O(n), as each character is appended once. In the average case, some duplicates are removed, but each character is still processed only once, keeping the time complexity at O(n). In the worst case, every character is part of an adjacent duplicate pair. Here, each character is pushed and then popped from the stack, but the total operations still remain proportional to n, resulting in O(n) time complexity. To solidify this, we can mathematically prove the big O bounds. If each character is pushed at most once and popped at most once, the total number of stack operations is 2n. This linear relationship guarantees an O(n) time complexity. Similarly, the maximum stack size is n in the worst case, confirming an O(n) space complexity. When solving this problem, there are several common mistakes to watch out for. One of the biggest pitfalls is relying on a brute force approach, where you repeatedly scan the string and remove adjacent duplicates in place. While this might work for small inputs, it quickly becomes inefficient as the input size grows, resulting in an O(n squared) time complexity. Instead, using an auxiliary stack allows you to achieve an optimal O(n) solution. Another common issue is neglecting edge cases. For example, an empty string, a string with only one character, or a string with all unique characters can expose flaws in your logic. Always include these scenarios in your test cases to ensure your solution is robust. Additionally, modifying strings inefficiently is another trap, especially in languages like Python or Java, where strings are immutable. Reconstructing strings repeatedly through concatenation or slicing creates unnecessary overhead. A better approach is to use a list or stack for efficient manipulation. Finally, forgetting to check whether the stack is empty before attempting to pop can lead to runtime errors. Always validate the stack state to avoid these issues. Overcomplicating the problem is another common mistake. Developers sometimes add unnecessary data structures like hash maps or overthink the logic, which only increases code complexity without improving performance. Instead, focus on simplicity by using a stack-based approach, which is both clean and optimal. From an interview perspective, this is an excellent opportunity to demonstrate pattern recognition. Problems involving adjacent or nested structures, like this one, often benefit from a stack-based solution due to its last-in, first-out nature. Be ready to explain why this approach runs in O(n) time and how each character is processed at most once. Interviewers may also ask follow-up questions about handling extremely large strings or streamed input. For such scenarios, you can discuss memory-efficient strategies like processing the string in chunks or using a two-pointer technique. Lastly, don't forget the importance of edge case testing. Highlight your approach to testing strings with no characters, one character, or all duplicates, as this shows thoroughness in validating your solution. This problem is closely related to several other challenges that also involve stack-based or string manipulation techniques. For instance, LeetCode number 1209 extends the idea to removing adjacent duplicates where a group of k duplicates needs to be removed, adding another layer of complexity. In LeetCode number 316, the focus shifts to removing duplicate letters while preserving the smallest lexicographical order, which also requires careful tracking of character states. LeetCode number 735, asteroid collision, is another classic stack problem where adjacent interactions are processed based on their order and direction, showcasing the versatility of stack-based solutions. Finally, LeetCode number 844, backspace string compare, involves simulating stack behavior to account for backspaces in strings. By exploring these related problems, you can strengthen your understanding of stack-based techniques and their applications in various scenarios. There are also alternative approaches to solving this problem, each with its own trade-offs. The two-pointer approach, for example, simulates stack behavior in place without using additional space, making it more memory efficient. However, this can lead to less readable and harder to debug code compared to the stack-based solution. Another option is the recursive approach, which repeatedly processes the string to remove duplicates. While the logic is straightforward, this method is inefficient due to repeated scans and risks stack overflow for deep recursion. It's generally not recommended for larger inputs. Finally, some solutions attempt to use hashing to track states during duplicate removal. Although this can work, it often adds unnecessary complexity and consumes extra space, making it less practical for this problem. When evaluating these alternatives, it's essential to weigh the trade-offs between simplicity, efficiency, and clarity to determine the best fit for the given constraints. Great job! To recap, we tackled the problem using an efficient stack-based approach, achieving O(n) time complexity. We also emphasized the importance of recognizing patterns and optimizing for both time and space. Thanks for watching, and don't forget to like, subscribe, and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!